A very good morning everyone. I am Shivani Garg, Assistant Professor from IIMT University. In previous two lectures of control system, we have studied about the basics of control system and mathematical modeling of the system. In this lecture, we will be studying about the transfer function modeling and block diagram representation of a control system. So let's start today's lecture. So first, what is transfer function? It is the ratio of Laplace transform of output to the Laplace transform of input while considering all the initial conditions as 0. So let's see if we have Laplace transform of input as us and Laplace transform of output as ys, then the transfer function gs would be equal to ys upon us while considering all the initial conditions as 0. So we have some steps to find the transfer function. First is to model the equations of the given system. So first we do mathematical modeling of the system, and then in next step we identify what is the output and what is input in the system, and then we take the Laplace transform while considering all the initial conditions as 0, and then we take the ratio of the output to the input. So finally we get the transfer function. So let's see one example. This is a simple RLC circuit, series RLC circuit. We have input applied VIT. We have a resistance, inductance and capacitor in series. We have output voltage across the capacitor V0T. So using KVL and using simple circuit laws, we get VIT would be equal to I into R plus L di by dt plus 1 by C integration of I dt, and similarly V0T would be equal to 1 by C integration of I dt. So first we have what we have done, we have computed the mathematical modeling equations from the given circuit diagram. So next step is to identify the input and output. The input is VIT and output is V0T, voltage across the capacitor. Third step is to find the Laplace transform of the equations. So first we and consider assuming all initial conditions as 0. So let's take the Laplace transform of equation number 1. So if this is our equation number 1, the Laplace transform of this equation would be equal to VIS R I of s plus S LIS plus 1 by S CIS, and the for Laplace transform of equation number 2, we note S would be equal to 1 by S CIS. So final step is to get the transfer function, which is equal to V0 upon VIS. So we put the values of V0 and VIS from here, and then we get the transfer function. So this is the method how we would calculate the transfer function of any given system. Let's see another example. So in this we have a differential equation, and we have to calculate the transfer function of the system. Well, so first step is already completed. We already have a mathematical modeling of a system. Second step is to identify the input and output. The input is output is y and input is u. So third step is to calculate the Laplace transform. So if we take the Laplace transform is this equation while considering all the initial conditions as 0, d cube d3y by dt cube, Laplace transform of this particular term is SQYS. So we have taken as ys as common, and we have taken the Laplace transform SQ plus 10s square minus 5s and plus 1, then us 10s plus 1. So we take the Laplace. Last step is to calculate the output upon input. So ys upon us is equal to this. So this is how we get the transfer function. So what are the properties of transfer function? Transfer function is independent of the magnitude and nature of the input. As you can see from this slide, this is the transfer function. It is independent of the input and magnitude of the input system. And using the transfer function, the response can be studied for various inputs to understand the nature of the system. So if we have a transfer function, let's say for example in this, we can study this transfer function with respect to the various input. We can apply different inputs and we can calculate the transfer function response for different inputs of this particular system. The next property is does not provide any information concerning the physical structure of the system. So two physical system can have the same transfer function. So a transfer function does not identify or does not give any significance comments on the physical structure of a system. So for example, we have a mechanical system and we have a series RLC circuit. we have for simple mechanical system, we have a transfer function 1 by ms square plus bs plus k, as we have seen in the lecture number 2, which is equal for m is equal to b is equal to k, it would be equal to 1 by s square plus s plus 1. Similarly, for series RLC circuit, we have output upon input, as we have seen in the example number 1 also, 1 upon s square LC plus SRC plus 1. If we put R is equal to L is equal to C is equal to 1, we get s square plus s plus 1. So these two transfer functions are equal, but this is a mechanical system and this is a electrical system. So both the physical structure of both the systems is different, but we can have a same transfer function. So the central form of transfer function is given here. We have mth order polynomial in the numerator and nth number polynomial in the denominator. We can also write it in the terms of fractions. We write as k into s minus z1, s minus z2, s minus zm divided by s minus p1, s minus p2 up to s minus pn, where n denotes the maximum power of denominator denotes the order of the system. So n is the order of the system, k is the gain of the system, gain factor of the system, a proportional value that relates the magnitude of the input of to that of a output signal at steady state. In Z1, Z2 up to Zm are the zeros of the system, at which the transfer function becomes 0. These are called the zeros of the system. And P1, P2 up to Pn are the poles of the system. The poles are the points at which the transfer function becomes infinite. So P1, P2 up to Pn are the poles of the system. When m is greater than equal to m, because the system becomes non-causal and it is not physically realizable if n is less than m. So it is observed that n is always greater than m. That means that degree of polynomial in denominator is always greater than degree of polynomial in numerator, because if it is not so, then it becomes a non-causal system which depends upon the future value, which is not a practically realizable system. So we always have n is greater than m. Poles and zeros, as we have seen in the previous slide, roots of the denominator polynomial of the transfer function are known as poles, where the transfer function becomes infinite. Okay, so these are called the poles. So for the previous equation, we have P1, P2 up to Pn. So total n number of poles. Okay, zeros, the roots of the numerator polynomial of this transfer function, where transfer function becomes 0. These are called the zeros of the system. And so in the previous slide, we have Z1, Z2 up to Zm. So total m zeros we have of the transfer function. Poles and zeros together with the system gain k characterizes this input output system dynamics. Gain poles and zeros example. So let's see one example. So we have a transfer function 6s plus 12 s cube plus 3s square 7s plus 1. We have a transfer function. We have to calculate the gain k, total number of zeros and poles, total number of zeros and total number of poles. Okay. So for this particular example, we have system gain k is equal to the constant 12 by 5. We can simply divide the constant terms by each other and we get the gain. For zeros, for numerator, for calculating 0, we put 6s plus 12 is equal to 0. So 6s plus 12 is equal to 0, then we get s is equal to minus 2. So this is a 0 of the system. And for calculating poles, we put s square plus s cube plus 3s square plus 7s plus 5 is equal to 0. So if we simplify this equation, we get s is equal to minus 1 plus minus 2j. So these are the poles of the system. So for calculating poles, we simply put denominator as equal to 0, and for calculating zeros, we simply put numerator as 0. So here we have 1, 0 and 3 poles for this particular system. So if we can see from this, poles and zeros are purely real or appear in complex conjugate. So we always have, if we have a complex pole, we always have a in conjugate form, plus minus. We cannot have only plus or only minus, we would always have complex conjugate poles. So next is the block diagram representation of a system. It is a pictorial representation of any system which considering the number of subsystems. So each functional component or subsystem. So if we have a simple, let's see one example. If we have a AC, so we have a block for AC. We have a controller, the temperature controller in the AC. So we have a temperature controller here. This is a subsystem, this is another subsystem. We get some output temperature, and then we take this as a reference. We have some reference temperature. Say suppose you have fixed the temperature at 18 degrees centigrade. So this is the simple block diagram representation of any system. So we have some subsystems, some sub blocks, and then we have output and input representation. So this is called the block diagram representation. Flow of signal from one subsystem to another. So these are this arrow shows the flow of signal from one signal to one subsystem to another one. Block diagram provides a simple representation of a complex system. So this is a simple representation of any complex system. It enables calculating the overall system transfer function, provided the transfer functions of each component or subsystem is known. So if the transfer function of these blocks are known, we can simply we use the some rules of the block diagram reduction, and we can calculate the transfer function of overall system. So let's see what are the components in a block diagram. So first one is the blocks. We have simple any block of a subsystem where GS is the transfer function of this particular subsystem. Another one, we have a component as arrows which shows the direction of information flows or signal flow. So these are called the arrows. Another one component is the summing point, which represents the summation of two or more signals. So if we have plus minus here, then you can take the U1 as positive and U2 as negative. So if we have plus, we can have this plus here. Okay. So this is simply adding or subtracting the points. Then another point is takeoff point, which it represents the branching of a signal. So if we want to take the any signal from to another block, so we can simply use a takeoff point. So let's see one example. This is series RC circuit. So here we have this VIT as input. So here in transfer function form, in Laplace transform form, we have a VIS, and we have an output which is V naught S. So we have a block with transfer function. What would be the transfer function? We can have we have a equation. From this we can simply calculate the transfer function using Laplace transform and mathematical modeling. We have V naught by VIS is 1 by S plus RC. So this block would be equal to, the transfer function of this block would be equal to 1 upon 1 plus SRC. So this is the block diagram representation of this particular system. Typical block diagram form. So we can have number of block diagrams in blocks in series. This is called cascaded system. So component or subsystem that are connected in series with each other is having its own transfer function. We have their own transfer function G1, G2 and G3, and these three are connected in series. Then overall transfer function would be equal to the multiplication of all these. So YS upon this output upon input would be equal to G1, G2 into G3. So if number of blocks are connected in cascade or series, we can simply multiply them and we can get the overall transfer function. So next is the feedback form, where we have taken a feedback term from the output form. So this here this is the block diagram representation for the same. So if we see this is the error signal, which is equal to US minus this is coming as we have taken as YS. So here we are getting YS into HS. So ES would be equal to US minus YS into HS. Okay, so ES error signal would be equal to US minus YS into HS. So now we have YS is equal to GS ES from this particular block. If we only consider this term, we get YS is equal to GS into ES, and then if we put the value of ES from here in this, so we get YS is equal to GS into US minus YS HS, and then if we simplify them, we get YS is equal to GS into US minus GS HS YS, and if we take the YS terms on the left hand side and US term on the right hand side, we get YS is equal to 1 plus GS HS GS US. So we finally got the transfer function YS upon US is equal to GS upon 1 plus GS HS. So this is the transfer function for the feedback block. This is negative feedback. So if we have positive here, we get a negative term here. Okay. So let's see one example. This is a separately excited DC motor. So if in this we have a applied voltage EA, armature voltage, we have a armature current, armature resistance RA, armature inductance EA, back EMF EB, motor torque TM, shaft displacement theta. This is a field circuit, as this is a separately excited DC motor. This is a field voltage EF, field current IF, and this is field inductance. So if we, so these are the specification, as I have already told. RA is armature resistance, inductance of armature, armature current, field current, voltage applied to armature, back EMF, motor torque, angular displacement of motor shaft. J is moment of inertia of motor and load transferred to motor shaft in kg meter square, and D is the friction coefficient of motor and load transferred to motor shaft. So and KT and KB are the motor and back EMF constant. So for this, so now let's apply the simple basic electrical equations for DC machine. We have EA is equal to RA IA plus SLA IA plus EB in terms of Laplace transform we have already calculated. So we can write it as EA minus EB is equal to RA plus SLA IA. So if we draw the block diagram for this particular equation, what we get, we have a summation point plus minus, we can give it as EA, this is EB 1 upon RA plus SLA is equal to IA. So simply we can simply write this equation in block diagrams form function as like this. Okay. So let's see for another block. Now we know torque is proportional to, motor torque is proportional to IA into IF, field current and armature current, and for separately excited DC machine we have IF as constant. So we can simply write it as Tm is directly proportional to Ta, or Tm is equal to Kia, okay, Kt Ia. So for this we can write in terms of a block diagram, this is Ia. So here we are getting IA. Now KT we get output as Tm. Okay. So now we are having output as Tm. So now theta is, sorry, So now we have Tm. If we see that in mechanical system, we have Tm as Tm is equal to J theta dot S, Js theta dot S plus D theta dot S. Okay. So if we take the theta dot S as common, so Js theta dot Js plus D theta dot S. Okay. So if we write this in a block diagram form, what we get is, we can simply draw next to it 1 upon Js plus D, and the output would be theta dot S. Okay, output would be theta dot S. So now theta dot S is equal to, we know theta dot S is equal to 1 by S theta S. So theta dot S is equal to S theta S. So if we write this in here in terms of this, so we get 1 by S and the output would be theta S. Okay. And now we know EB, back EMF, is equal to N P phi Z upon 60A, where P is constant as field current is constant, so phi is constant, number of conductors Z is constant, 60 is constant, A is constant, so E is directly proportional to the speed, N is speed, which here we can write it as EB is directly proportional to theta dot S, okay, or EB is equal to KB theta dot S. Okay. So finally we get the transfer function this. So we have EA. EA is, and here it should be EB as we have calculated, EA minus EB. So this should be EA minus EB, which is equal to 1 by LS plus RA is equal to IAS, and IAS is equal to TM KT, and TM is equal to S theta S or theta dot S. This is equal to theta dot S, or theta dot S 1 by Js plus ds, and this is equal to 1 by S, integration of this is equal to theta S. And similarly the theta dot S or speed is given here, it is theta dot S, and theta dot S into KB is equal to EB. Okay, theta dot S KB into theta dot S. Okay, so what we are getting here, so this is the transfer function using all the equations. We have first calculated the mathematical modeling and then we have converted it into this block diagram. We can calculate, simply calculate the transfer function. These three blocks are in cascade, so we can simply multiply them, and then so what we get here is 1 by LS plus RA plus into KT into 1 upon Js plus D. Okay, and then 1 by S, and output is theta S. Here we are taking it as KB plus minus this is EA. Okay. So this is a block diagram of feedback transfer, negative feedback. So we can simplify it using this, the negative feedback as we have shown previously, and then simply multiply by 1 by S. So we get transfer function theta dot S divided theta S is divided by EAS is equal to this. So this is how we calculate the transfer function from the block diagram. So this is it for this lecture. In the next lecture we will be seeing how to reduce the complex block diagram form into a simple block diagram, single block diagram form and signal program. Thank you.